a number of other resources to be very productive. But in a data science perspective, a lot of those things are pretty lacking, especially in some areas of tooling. There's not several well-defined methodologies and so on. So from those experiences, consulting and so on, I saw some things that worked, some things that didn't. And this is basically a number of lessons learned in several different areas of conducting machine learning, from collecting data to managing data sets to training your models, deploying, and so on. So these are basically a number of lessons learned and a number of tactics that have worked very well. So I want to start from the scratch, starting from how you collect your data and a number of things that have worked and haven't here. One of the main things that come in practice when you're working on those projects, especially early on, is that when you're working with deep learning, you require massive data sets, but if it's a new company, a new product, you might not have that data yet, especially since sometimes you have to label that data. So you might have the raw data, but you don't have the annotations and so on. So in a lot of cases, you basically have to start with small data learning. If you're coming from, let's say, a research background or from a research perspective, there's a lot of work in actually dealing with small data sets and still leverage those very large models with very small data sets. So, for example, in the last CVPR conference, which is one of the large computer vision conferences, there were about 20 papers that were published just on zero, one, and few shot learning, which is basically learning from zero, one, or few examples for different classes and so on. And there are a number of techniques here, so metric learning, meta learning, data augmentation, semantics, and a number of different areas on how people are trying to tackle this. But often in practice, they are very complex methods. They're still research-oriented, experimental. So in a production setting, it's a lot often easier to just go ahead and collect more data and label more data yourself. If you actually spend one day labeling data yourself, it's going to be a pretty boring day, but you're going to be able to get thousands of good data points, so you're going to be able to break that barrier of few-shot learning and so on. And in a lot of cases, you might then consider, okay, we might not have the data or even the raw data, so labeling isn't the issue itself. So in those cases, you might want to get creative into how to get those data points. So you might want to simulate the data yourself. You might want to, let's say, scrape data elsewhere, get from existing data sets, do some sort of transfer learning, and so on. And this can help basically simplify the process a lot. Instead of having to deal with those very complex experimentals and few-shot learning, you can actually do traditional machine learning like this. So as a practical example, from my research in the computer vision lab I mentioned, the idea behind the research was to use LiDARs, which is basically laser sensors that measure depth, to understand what's happening in ICU rooms, so hospital rooms. And the idea there is that we wanted to do that in a way that protected patient privacy and so on. So the main challenge we had is that a lot of the computer vision methods and the available data sets, they're based off regular RGB cameras, but those wouldn't work for use case. We wanted to use this novel sort of data. So from this sort of data, there's very little data out there. We had a very small data set, and actually labeling this data set required, let's say, nurses or medical professionals and so on. So it was a pretty challenging data set to actually get a substantial amount of data. So what we actually ended up doing that actually helped the performance increase a lot and really grow the model was that we actually simulated a lot of the data ourselves. So we actually flew into the hospital. We got an empty room for a day, we installed all the sensors, and during the whole day, we're simulating a lot of patient activities. So in this case, for example, I played a patient, I played a nurse, I played several different roles there. My peers, coworkers, we were getting in and out of the bed, receiving fake treatments, and a number of different things. So from a single day doing this sort of simulations, we were able to collect hundreds of data points from a data set that we had a couple hundred before. So we more than doubled the size of the data set by doing something like this. So this is a strategy that can be used in a number of different settings. Another problem that comes up very often is that basically people collect a very large number of data, and this data might be very noisy. So especially if you use, let's say, crowdsourced annotations like Mechanical Turk or some of their more common modern counterparts like SageMaker, Ground Truth, and so on, a lot of the labels are still very noisy, especially if you have a single labeler for all of those. And even if a lot of your data is pretty good, but let's say 10% or 20% of it is not good, you're not going to get very good results. Having a smaller, cleaner data set is going to give you a better model, and also allow you to validate the model very well. If your model is already pushing, let's say, 80 or 90% performance, you can't really measure well the last 20% if 20% of your data set is very noisy. So you actually might be making mistakes, you're picking the wrong model or making the wrong optimizations because it's just randomly making better predictions and noisy data points and so on. So it's actually, in a lot of cases, more helpful instead of working with very large data sets or just trying to easily get as much data as you can to have a smaller data set, but try to do that in a way that you have cleaner labels and so on. And in a lot of ways to do this, there are different approaches where you can start to tackle this. For example, you can start with a trusted labeler that could be yourself or another coworker or so on, where you know that the labeling is going to be very accurate and they can label a small subset of the data set or they can audit a part of the data set to evaluate if it's actually properly labeled. You can start with like a larger set of untrusted labelers and then have a reviewer merge or pick the correct one and so on. So if you use crowdsourced, let's say, Mechanical Turk labeling, you could have 3 labelers label each of the data points and then have a reviewer, which can also be a crowdsourced worker, basically vote on the correct one and so on. Or in addition to this, or instead of doing this, you can also use multiple labelers to get these noisy labels, and then actually use some sort of algorithm to merge them. So for example, you could have some voting algorithm. Let's say if the 3 labelers agree, then you consider a label. If they disagree, then you manually label that yourself. If it's, let's say, bounding boxes, if the bounding boxes have very high overlap, again, you accept that. If they don't have high overlap, that might be a tricky case, so then you label that yourself. I think one of the important caveats here is that one of the obvious things that people might want to do is that, okay, if the labelers don't agree among each other on a single data set, let's discard that data point altogether. The challenge with this is that a lot of the tricky data points, which are very important for learning, they might be tricky for the labeler too, so that's where they will make most of their mistakes. So if you just start discarding all the data points where they disagree, it might be the case that, okay, this is a very tricky data point that would be very helpful for us to have. So it's actually helpful to have then a reviewer actually manually go and check the ones that were discarded and label that themselves. Or potentially have a new batch of labelers look at that again and have, let's say, another 3 labelers relabel the data points instead of just fully discarding it. So with approaches like this, you can first create a larger data set than expected with simulations, scraping, translations, and so on. And then using approaches like this, you can have a very clean and relatively small compared to large noisy data sets, but having a relatively moderately sized but clean data set allows you to learn in the best way, and then especially so when it comes to validation. You can have very good certainty that your model is actually performing as expected, the accuracy or whatever other metric you're looking for, it's actually what is being reported rather than something that's lower or higher because the data set is noisy. So once you have this data, a lot of the challenges then come up are regarding managing the data set itself. So one of the main challenges is that when you're dealing with code, you can just use some version control, let's say like Git, and just keep pushing the code, and if anything goes wrong, you have the whole history. It's easy to collaborate and so on. But let's say you have, let's say, 2 terabytes of video data or some other complex sort of data. You can't really push that to GitHub. There are some workarounds. You can use, let's say, Git large file system and other things like this, but they don't really play well nicely with those massive data sets. So what really ends up happening in practice is that those data sets, they're in, let's say, S3 buckets or equivalents for other providers. They're in very large data stores. They're in like SQL databases and so on. And in a lot of cases, those data stores aren't really version controlled. And this brings a number of challenges for practitioners. First is that as you're dealing with your own experiments, you might add new data. Let's say if you have a database that's connected to production, you might get new rows all the time. Rows might get updated and so on. So if you're comparing 2 models and you're basically using different sorts of data sets or different versions, then the metrics might not be comparing apples to apples. So they might not be accurate. And even though, okay, you're seeing that your model is getting better and better, it might just be because you have more and more data, not because your model is actually improving intrinsically. This gets especially challenging when you're working with, let's say, teammates, because even though you might have the same original data source, some teammates might add additional data for their experiments. They might also, let's say, clean up some data, clean up some labels, correct some data points, and so on. So each practitioner has different data sets. So as you're sharing code or comparing models and so on, it becomes a much larger challenge than to ensure you're all working in the same place. There are a couple commercial solutions out there, but in a number of cases, relatively simple solutions that already work pretty well. So for example, a solution that I've seen in a couple companies that are doing this pretty well using some of their internal tooling is first when you're running an experiment or let's say training a model or something like this, it basically timestamps all the data points that are going into this training process, let's say your training set and your validation data set, and then also so let's say computes the hash of all the data, and basically stores that in some sort of log and so on. So having this hash that you can compare against later, if you're running a different experiment, or let's say a teammate is going to run a different experiment with a different sort of data, those hashes aren't going to match. So if you have, let's say, a log or some sort of store of your experiments and what sort of data it came to use, you can at least know that, okay, something happened with the data, you're not comparing apples to apples. And if you set up your data store, let's say, such that S3, you're just storing older and older versions. You're never overwriting or removing older files, just updating the state of the bucket. Then you actually go back and retrieve the older files or whatever you might need. And especially since you're also using this sort of like timestamping log, you can basically store all the data points that were used. If there are new data points, you can know which ones were used. If some of them change, you also know by the hash which ones change and so on. So it's a relatively simple tool you could build into your own, let's say, R&D pipeline that actually lets you solve this problem fairly easily. So now, once you have this data set, a lot of the work that goes into the work of, let's say, a data scientist is actually building data pipelines and pre-processing scripts and so on. If you're doing the data pipelines for production, there are a number of solutions out there. Let's say Airflow and a number of cloud vendors have their own solutions. But during the actual R&D process, those solutions add a lot of overhead. So in practice, most data scientists don't use those when they're creating the model or experimenting. They just use that once they know what they want to do and want to push that into production. So first you have this gap that your training and R&D code is very different from your production code. And second is that during this R&D process, since you're basically using you're not using off-the-shelf products, you're basically reusing our codes, you're using a bunch of, let's say, Python scripts and so on, you actually introduce a lot of mistakes. So if you start optimizing your pipelines, you could, for example, look into parallelizing your code, or you copy-paste different solutions from previous pipelines, and you start introducing potential bugs. There are often no unit tests and so on. You basically have this spaghetti code that you copy-pasted from a number of previous pipelines, from code examples online and so on, and they might not merge well together. So for example, one of them might expect RGB images, another might expect BGR images, and then there's no error, there's no alert when this mismatch happens, and you only see at the very end that your model is not performing very well. And it might actually perform to some extent, so it's actually not trivial to debug where all those mistakes came from. So one thing that is actually very helpful is that as you build this pipeline, it's often helpful to include some data sanity tests along the pipeline. So at each stage, you're basically checking if each data point or each column or whatever you're working with is actually what you expect. So let's say in a simple example, let's say you're working with SQL data, some data sanity tests that we could use during those pipelines is checking, for example, are the values in a range we expect? So for example, for age, we shouldn't have negative integers. How are you dealing with missing values? In a lot of cases, libraries and so on have a default value for the missing value. So it could be, okay, we're going to map all of them to 0, but in this case, it might not be that helpful. So having checks for those and how to deal with them. There are a lot of cases where you have, like, say, mixed data types. So if you have integers and floats, how do you deal with those? And in a lot of cases, it might play out nicely if you mix data types, but in some cases, there might be edge cases for those pre-processing scripts where it might be expecting some sort of data point in a certain data type, and if it receives something different, it might behave in an unexpected way. So this is looking at the specific individual data points, but it's also interesting to look at the whole distribution itself. So for example, let's say there was a bug in the code that just mapped all the age values to 18. If you look at the individual data points, that's all perfectly fine. But then if you look at the whole column, that's actually a problem. So if you have some expectation for the distribution of your data, let's say, okay, the mean should be somewhere in this range, and we should have some sort of standard deviation, or at least, let's say, 10 unique values, or whatever statistics you can compute. You can add some checks to ensure there's at least some sort of variability, some sort of distribution as you expect. The standard deviation for, let's say, age shouldn't be 1,000, and at the same time, the mean shouldn't be several hundred, and other things like that. So you could have simple tests to make sure they're relatively within boundaries, and if some bug occurred, you can spot that very early on, not after you train your whole model and it's not performing very well, and it's hard to debug where the bug came from. And you can do that for the data point itself, but it's also important to do it the same for the label. So for example, again, if the whole labeling system had some sort of issue that then mapped everything to false, or has something that it's extremely imbalanced, you can find that very early on before you actually spend a lot of time training your model, debugging the model, and so on. And especially as you're working with those distributions, there are some pretty nuanced errors that often go unnoticed, but it's actually very important. So for example, if you have some sort of model that's based on click-through rates or something like this, if the website was offline for a day or two, or if there was a problem with the login infrastructure, the whole distribution might look fine. Where for subsets, for example, by date or by some other grouping you can think of, you can see some interesting patterns there. So for example, if the website was offline, or this particular service was offline for 2 days, you might get a 0% click-through rate, which is probably unusual and not something you should see. But in the whole distribution, it's fine. The individual value is fine. So this is something that might be helpful to inspect for and group by date, by user, by cohort, or whatever might make sense in your data set. Something else that's interesting and also very important for us to look at is that data sets and data patterns evolve over time. So for example, if you're looking at clicks in a website and the website is growing over time, then the values might also, the distribution of values over time has changed a lot. So for example, over the span of 9 years, your website might go from a very small niche website to a very popular website. So in the span, if you're basically training your model from your early data and then evaluating your more recent data without acknowledging that at least there were some changes in how this data distribution plays out, then you're going to get some poor results. So at least checking for different patterns like this, and if they exist, acknowledging them and potentially trying some techniques to tackle them is something that's important to have there. But often people just don't really monitor this, and it goes unnoticed, and it's something that only comes up much later on when we notice problems in production and so on. And in a lot of cases, when you're working with, let's say, tabular data, it's more straightforward to deal with tasks like this. But this is also important in other areas. So let's say, if we're working with computer vision, there's a very common bug that I see in a lot of computer vision systems, is that there are bugs in rotations based on the metadata of the image. So for example, an image like this, it could actually be a landscape image that's wider than taller. And the reason this happens is that there's this thing called the EXIF metadata, which is basically a number of metadata that's included in JPEG images that could say, okay, rotate this image, but in memory, the image is actually in an horizontal position, for example. A lot of cameras, instead of actually storing the image vertically when you take the image vertically, they'll take in the same direction as the horizontal image and just store this extra flag saying, okay, rotate this by 90 degrees or something else like that. The problem is a number of libraries see this metadata and rotates the image for you, but some libraries don't. So often problems I see is that, okay, your let's say, Mac image viewer is going to show the image as expected, and then you upload it to, let's say, Mechanical Turk, and there the image is displayed horizontally, so the labels are in this different dimension. But then when you download the labels and start using it again with, let's say, OpenCV or TensorFlow, they actually acknowledge this metadata, so it's back in the original position. So the image looks fine, your labels are completely off, and you don't really know where that comes from. So it's often helpful to also add tasks that check for properties like this. You could also check for, okay, if I'm expecting an image that's horizontal, is this aspect ratio actually like that? Are the dimensions that I'm working with, the number of channels, is this RGB, and a number of other properties that you're expecting. You can add this sort of sanity check into your pipelines, to your model, and actually discover a lot of those errors early on. And then you finally get to the actual R&D stage where you're creating your model. So you basically collected the data set, you stored the data set, managed to pre-process it, and generate all the features. And again, testing is extremely important for the model itself, and it's actually pretty hard to debug a lot of deep learning models. So one of the things like I mentioned right now, checking for the input validity is something that's extremely important. So your model might be expecting something different from your pipeline. Your pipeline may say, okay, I'm going to output images that are 100 by 100 in RGB. Your model might expect 112 by 112, and there's some sort of bug, and that goes unnoticed. In a lot of those libraries, they will actually not report small changes like that and try to do some clever optimization, but it might actually do something that's not what you're expecting. It might resize the image, but not the labels, and there are a number of issues like that. So actually checking that the input is exactly what you want and the format and so on that you need, it's something that helps a lot and helps you catch a lot of bugs early on. Something else that's helpful is adding unit tests to ensure all the variables and the outputs are in the same dimension as you're expecting. Especially since, let's say, NumPy and TensorFlow and so on, they broadcast the dimension. You often can basically play with different dimensions, and it's not going to output something that's nonsense, but it's not really what you expect. So let's say if at the end of your model there's some sort of averaging and so on, if you're playing with different dimensions and wrong dimensions throughout the model, you're not going to notice unless you actually check the intermediate steps. So having those unit tests, which very rarely come up in data science, actually help you spot those errors very early on. It's also, like I mentioned, important to look at the outputs and some of the intermediate outputs if you can, and make sure they're sensible. So is this distribution what you're expecting? If you're expecting a probability, it should be, let's say, between 0 and 1. And if you see something outside there, there might be some bug in the model. So having those sanity checks for the ranges of values, the distributions, you could, for example, generate random data and feed that through your model, or get like a random batch and feed that through your model and make sure, okay, are all predictions the same, or are they predicting different values and so on. If you see, let's say, for any sort of image, it's always predicting the same, let's say always predicting 0, or whatever that might be, there's often a bug in the code or something like that. And again, something that's often helpful is that there might be very nuanced bugs in the code where instead, when you're building the model graph, let's say for deep learning, you might skip a variable, or you might create a layer, actually not use that in your model or something like this, in a way that, let's say, all your layers are incorrectly based off the input data instead of the previous layer's output. And by having some sort of check that, okay, you feed a single data point or a single batch to your model, and then you ensure that every single variable that should be changed actually changed by a little bit, you can spot those errors in defining the architecture. And likewise, if you're dealing with some architecture that shouldn't change as a whole for every step, for example, let's say you're working with a GAN where you have two networks, you have the generator and the discriminator, and only one of them should change at a time. You could have the same sort of test where you feed a batch to the discriminator, you ensure that all the variables for the discriminator change, but none of them for the generator changed, and then vice versa. And then you ensure you haven't accidentally reused some of the weights, you haven't accidentally, let's say, forgotten to initialize some of the weights, so it got the default ones from the other network, and so on. So having those sort of tests can help you spot very nuanced and very hard to debug errors very early on. And like I said, it's also helpful to look at the sanity test for the outputs of the model itself. So for example, if you take a data point that's extremely obvious and feed that through the model, you should get at least for a trained model that works reasonably well, you should get the output that you expect. So if you, let's say you're dealing with credit and you're predicting, okay, for someone with awful credit, they're asking for a $10 million loan, and you feed that to your model, the model should say reject. And you should have some pretty obvious data points that should be able to notice very bad mistakes. So if your model is working very incorrectly or failed to train or something else happened, or might be a bug in the output or something like this, if you feed a couple extremely obvious examples, it should at least pick up if it's failing to at least get those correctly. And also, as you're developing those models, it's important to keep in mind not only about the bugs, but also what goes into training the model and what goes inside the model. So if you have, let's say, a baseline that someone on your team or even yourself created that had 87% accuracy, and now you're training a new model for, let's say, a new architecture you just read on a paper, and it's 82% accuracy, it's not necessarily that this model is worse. If the previous model, you already conducted very extensive hyperparameter search, You did a lot of data augmentation, and by experimenting a lot of the same model on the validation side, you're basically overfitting a little bit to this validation data set, and a number of other techniques. You can actually get very high performance on this original model, even though if you were comparing both models without any of those bells and whistles, it would have performed worse. So if this new model, without any of those bells and whistles, actually performed relatively close to the original model, it might actually be the case that if you actually do all this hyperparameter search and all those extra techniques on the new model, you might be able to beat the original one. So this is something that often goes undocumented. You're not really sure what's in your baseline, what you're comparing against. So it's actually very helpful and very important to document what goes into each of the models, what sort of data set did you use to train. Is it just a standard data set? Did you have extensive data augmentation? Often you get 5% or something like this in like free extra performance just from augmentations. Hyperparameter tuning, something about the same. So you can get sometimes, let's say, 10% extra performance just from those extra techniques that are applied later on. And again, beyond just then training the model, when you're deploying the model itself or A/B testing in production, there are also a number of other things that come up that are very interesting. So monitoring and A/B testing is also important for the models themselves, not just the whole application. Often people only focus on monitoring the model metric itself, so the accuracy or precision or whatever is being outputted by the model. But it's actually important to go beyond that and look at some other metrics. So for example, we could look at the application performance, which basically means how the inference speed is being reported. And again, when people look at this, people are often only concerned about how fast the model itself is running, not how the whole application is running. So for example, it might be the case that the calculation of the model itself runs very fast, but there's a problem with how you load the data or store the outputs or something like this, that as an end-to-end system, it's getting worse and worse or has some problems, or in some edge cases might not work very well. So not only you should look for the model's speed, but also the end-to-end system, and not only look at the average speed, but as you're doing traditional application performance monitoring, look at, let's say, the 95 percentile, the 99 percentile, to understand how your model is really performing on edge cases. This is often a problem with, let's say, NLP models, which a lot of cases when you're, let's say, decoding the output, that's an ON squared or ON cubed, or sometimes even worse, algorithmic performance. So a lot of cases, the developer or practitioner tested this on a, let's say, 5-word input or like a 1-sentence input, and then user inputs 1,000 words, and the model completely breaks or crashes the system or is extremely slow. So actually monitoring those edge cases can help you, give you some insight. And if you see, okay, in the 99 percentile, it's actually very slow, you can actually then log those cases and see, okay, what are the inputs that were used here? What are those edge cases that are actually helping the model crash? And then you can use that to optimize or to refactor, debug, and so on. And then beyond all this, it's also important to look at the business metrics, like conversion rates or whatever might be helpful for your application. And since even though you might be improving the accuracy or whatever is in the model, you might actually not see any actual improvement. So there might be higher order effects that, for example, your recommendations are very good now, so the user never actually goes to the shopping cart or something like this and doesn't buy, or there might be some confounding variables where it's not actually the accuracy that leads to higher engagement or higher performance. It's actually the inference speed. The model is slower, so there's lower engagement. So there might be a lot of factors like this. So actually understanding how the model affects the end metrics, so your KPIs or whatever that might be, basically without concerning the actual metrics of the model, might be very important. So as a couple examples from practice, in terms of like performing application monitoring, an example I've seen is that the model sometimes will leak data or leak memory or whatever that might happen here, where the performance is very good for the first 2, 3, 4 days, but this data leakage or memory leakage starts to accumulate, and then over time, which might be a week later or 2 weeks later, the model starts getting slower and slower. But if you only, let's say, profiled your model early on during R&D or just as you launch it in production once, you're going to miss those trends over time. And then in this case, the model that was leaking data eventually will crash the server or the model or whatever that might be. So it's important to have this longitudinal overview where you see how this performance is evolving over time. It's also important to see how the performance of the metrics the model evolve over time. In a lot of cases, the model might get stale, or the novelty that the model introduced might be gone. So for example, if you're doing a recommendation system, just changing algorithms might introduce some novelty, which then increases engagement early on, but that might decrease later and later on. So by monitoring this, you can look, okay, I see this is starting to drop, might be time to refactor this or try a different model, different factors and so on. So keeping this in mind also helps. The main challenge that we have when doing this is that in a lot of cases, if you add a lot of novelty to the application, then there's this warm-up period where users are still getting used to the changes. So if you change the UI a lot, or however the application or product is being used, it might take a couple of days or a week or two for the users actually to understand and learn how to use those new features. And it might seem early on that, okay, oh, like performance is worse now, let's kill this model, but the model is actually still warming up. So this is something that you need to be mindful of and check that if this is something that happens and if it's a very meaningful change, it might make sense to have a longer period where you might use, let's say, a smaller subset of users, but then have this test run for like a week or two to see how this warm-up works. And if you see that they actually warm up and then finally started getting stale, then you can use that data point as how to compare for A/B tests and so on. And then beyond all this, a lot of people, especially with data science practitioners, and I'm guilty of this too, is that when I see a problem, I want to use the latest research, the biggest models, the most interesting ways to tackle this, but that's actually not the best way to tackle it in a lot of cases. Depending on how much data you have, a different number of techniques might be useful. If you have, let's say, very little data, traditional machine learning techniques from a linear regression to an SVM or whatever that might be more accurate than actually using this like huge machine learning model, deep learning model. And even when you're working with deep learning, the amount of data is going to influence which sort of architecture and what sort of parameters and so on you're going to use. If you have a relatively small data set, you're not going to use, let's say, 150-layer convolutional neural network. But if you have, let's say, 1 million data points, then it might make sense here. So if you actually consider how much data you have and how much data you might have in the future, you could start with relatively smaller models and simpler models and have this evolve over time. And then you're working from this frontier where you're working always with the bigger and bigger models, more and more complex ideas. So you both get to start with something simpler and then over time get to something more complex. And then you're also always in this ideal frontier where you don't need as much data, you can start quickly, deploy faster, and so on. So as an example, if you're working on a project for, let's say, detecting brands, one of the obvious ways to do is to go ahead and download a bunch of ads and label all those bounding boxes and objects and logos and so on. But a much simpler way, if you're working with computer vision, for example, is to do some sort of template matching. You get 1 or 2 or 3 examples per brand or per item that you want to have, and you do a simple computer vision-based template match or SIFT, which is a relatively old technique, a relatively simple technique. You're not going to get state-of-the-art performance, but it's going to give you decent performance. As you can see here, you can get items that have, in this case, slightly different rotation, some occlusion, some sort of shading, and still get some reasonable performance. And then you can start with something like this, and as your model is in production, and as you get more and more data, more and more annotations, you can then shift from something like this to, let's say, a deep learning-based object detector, and so on. And in a lot of cases, you can use very simple rules or heuristics just to get started. If you think there's a simple heuristic that can do, let's say, half the job, it's often helpful to start with it and try out the product and see how it's working. And if you do that, then one of the interesting things that can happen is that the heuristics that you're using themselves can actually help you engineer the features for the models that you're going to use later on. Especially if you're not going to jump directly into a massive model that takes your raw data and makes the prediction. You're going to use a smaller model that takes some feature engineering, some manual work. The rules and heuristics that you created, let's say a number of logins in the past 30 days or whatever that might be, that might help you actually create those features and engineer those smaller models and get pretty good performance. So this is often a pretty good step to start with. And in a lot of cases, especially in a number of tech startups, they start with something that they call the Wizard of Oz experiments. So this is a term from human-computer interaction research, which is when you simulate some technology and so on by actually having a hidden human perform the work. So this is an example from history where they had this chess playing machine that was actually a person that sat inside the machine and then played the chess without and it looked like there was this automaton, like a robot person that would play the chess. And in practice, we see this very often. So for example, a company I was familiar with called X.AI, they had this AI to your virtual personal system. It would do scheduling with emails, respond to those sorts of emails, do the back and forth, push on your calendar, and so on. And early on, it was actually a team of remote people. They had a large team in the Philippines, actually working 24/7, dealing with those emails. And basically, by having them actually solve the problem manually, they're first actually solving the problem for the user, so they weren't actually lying and cheating the users. They're solving the solution. But they're actually getting the data to train their models later on. So by having people manually do all the work, they had the data that they couldn't otherwise get. And then once they started scheduling, extracting these labels for like dates and locations and whatever it might be, they could then train their own NLP models to help improve the performance of the team. And eventually more and more was going to be handled by the model and less by manual labor. So they could have the same small team be more and more efficient, scale to much larger sets of users, and so on. So even though it's something that's initially fake, it's still useful for the consumer and helps you get the model. So this is some of the things I want to cover. I'm happy to answer any questions, and please feel free to ask me later or email me or anything like that. Thank you.